Welcome, welcome back, everyone. For today's main seminar, we have Jamie Bell from the University of Munster, also, who will be talking about stable rank 1 in non-nuclear cross products. Take it away.
Thank you, Ben, and thanks for the invitation to speak here. Thanks also, Malta, for giving the wonderful pre-seminar talk. Basically, all the hard work has been done for me, and I can just, elaborate on some of the topics that were introduced in the previous talk. So yeah, indeed, I'll be talking about this recent joint work on stable rank 1 in non-nuclear cross products, which is joint with Shirley and David. Yeah, I mean, some of the terminology and notation has already been introduced, but let me just fix some notations and assumptions. So the setting will be as follows. G will always be a countable discrete group. X will be compact metrizable. And in fact, often it will be a Cantor set towards the end of the talk. And then we have an action by G on X by homeomorphisms, which, unless I say otherwise, will always be minimal and topologically free. And then we recall that associated to this, there is the reduced cross product C-star algebra, which under these assumptions will be unital, separable, simple, and again, as explained before, whenever the action preserves at least one invariant measure. So this is my notation for the set of G invariant measures on X. The C-star algebra will be finite. Okay, and in particular, for G being non-amenable, this will force the cross product to be non-nuclear. Okay, so this is the general setup, and then the overarching problem, which occupies many people's spare time, is rather vaguely which conditions on this action give rise to, let me say, regularity of the cross product. Okay, and to give you some idea of what I mean by regularity, coming from Munster, I of course need to mention classification at some point. The kinds of things I have in mind are finite nuclear dimension, so like stable rank, this is another way of describing a non-commutative version of covering dimension for C-star algebras. And this is one of the crucial inputs to the classification program. Very relatedly to that is so-called Z stability, which means that, okay, tensorially you absorb this mysterious object Z called the Jiangsu algebra. And yeah, under these other assumptions, as well as nuclearity, these are the critical things to give you classification. So it's, of course, important to be able to check these in examples, such as for cross products, so that we can use the classification theorem. Sure. It doesn't really have a definition. It's vague. So I mean, a whole category of different properties that a C-star algebra might have. And these are particular examples of what I have in mind. Yeah, so this is sort of elaborating on this. Plus other stuff. So by other stuff in particular, as the title suggests, also stable rank 1, we would count this as a regularity property. So it's rather vague, but it's some nice property that we would like our C-star algebras to have. Okay. Cool. So why do we care about stable rank 1, which throughout the talk I'll just abbreviate as SR1? And the point is that this is not one of the main assumptions or regularity conditions going to classification. However, it's a very useful kind of auxiliary condition that you should think of as something weaker than the other two. But it still has some very nice consequences. So the original motivation, so this concept, I should say, is due to Riefel in 83. And his motivation for introducing this was the study of so-called non-stable K-theory. So for those of you who are familiar with K-theory, you know that it's a very important invariant for studying C-star algebras. This non-stable K-theory is somehow investigating finer properties of this K-theory. And it turns out that stable rank 1 gives you a lot of extra flexibility when studying K-theory that you don't have in general. So for instance, I have in mind things like cancellation of projections, and also what you might write as K1 bijectivity. So this means that K1 is canonically isomorphic to unit trees in A modulo the connected component of the identity. So somehow you can express K-theory, which is a stable object, right? This is expressed in terms of elements of A tensor K, just in terms of A itself. So this is somehow the original motivation. And in more recent years, a sort of trend has emerged that stable rank 1 is also very important when studying properties related to the Kunst semigroup. So I won't define this here. It's not important for the rest of the talk. But let me just say that this is a very rich invariant associated to C-star algebras that somehow contains K-theory, maybe not K1, but at least K0, and also contains information about traces and the ideal structure of your C-star algebra. So it's important to be able to understand this object if you want to understand the C-star algebra. And stable rank 1 somehow gives you a lot of extra tools in the Kunst semigroup that you don't have for general C-star algebras. And let me just list some consequences that you have. So for instance, somehow the subequivalence or Kunst subequivalence that goes into the definition of this object. This is unitarily implemented. So already in defining the Kunst semigroup, somehow in the stable rank 1 case, it more closely aligns with the definition of Murray von Neumann's subequivalence. And this has also led to the resolution of a number of important open problems for C-star algebras under this additional assumption of stable rank 1. So for instance, realization of ranks. And this is originally due to Hannes in the simple setting. This has the consequence, for example, that ASH algebras of stable rank 1 satisfy the Thomas-Winther conjecture. Okay, which is another thing connected to the structure of the Elliott classification program. This is one of the key outstanding open problems. Somehow, most of the results prior to this had some restrictions on the size of your trace space. And here, under this weaker assumption of stable rank 1, you can actually encompass a much larger class of examples. And as another instance of the importance of stable rank 1, for those of you following the archive newsletter this morning, this also came up as a critical assumption in the resolution of the question of whether Wilitzen type 1 algebras have uniform property gamma. Right, so if none of that made sense, that's fine. It's not important for the rest of the talk, but I at least want to motivate that there are important reasons to understand when a C-star algebra you're interested in has this condition of stable rank 1. Okay, any questions before we move on? Cool. So let me just, yep.
The concept block is related to extending classification outside.
Sure, yep. I'm not the expert to ask, but for instance, the Kunz semigroup remembers the ideal structure of your C-star algebra. K-theory, I mean, you can take any contractible space you like of any dimension. These are always going to have the same K-theory. So it somehow, at the very least, holds on to more information than K-theory alone. Yeah, this is one motivation.
What's this realization
Right, so well, the definition is a little bit hard to describe, but somehow to each element in a C-star algebra, you can associate a dimension function. Sorry, to each trace on a C-star algebra, you can associate a dimension function. And you can somehow ask whether all of these are realized by a certain rank function associated to an element in the Kunz semigroup. Yeah, it's maybe a little bit too much to write down for this talk, but I'm happy to discuss it later. Yeah. Cool. Okay, so let's move on now to get a little bit more of a feel for what kind of C-star algebras have stable rank 1. So I want to give a couple more examples. The first were already introduced in Malta's talk. So first of all, it's easy to see that all matrix algebras, and therefore more generally all finite dimensional C-star algebras have stable rank 1. In the commutative case, these have stable rank 1 precisely when the covering dimension of X is at most 1. And then combining these two together and using the permanence properties that were described in the previous talk, all AF and AT are approximately circle algebras. These also have stable rank 1. But the purpose of this talk is to discuss cross products. And already this third point actually gives you some examples of cross products that have stable rank 1. So a kind of corollary, although this is overstating it a little bit, a corollary to this is that if you take any irrational rotation algebra, this is proved by Elliott and Evans to be an AT algebra and therefore has stable rank 1. And also you can take any minimal homeomorphism of the Cantor set this is due to Putnam. These are also AT algebras, and so in particular have stable rank 1. And I mean, one of the trends in classification and more generally in studying C-star algebras often follows a similar line of inquiry here, where you start by understanding simple building blocks. You show that you can approximate the C-star algebra you're interested via inductive limits of these simpler building blocks. And then you hope to show that the objects themselves inherit that nice property. And indeed, that's also the case with various stable rank 1 results. But if you want to go beyond Z actions, this sort of quickly runs into difficulties, because trying to directly show a direct limit decomposition of cross products of, say, arbitrary amenable groups is going to be a very difficult task. And so you want to somehow abstract away what the key condition is that that gives you stable rank 1. So coming back to this notion of regularity, this is partly what I mean. It's sort of what's the right abstract notion that captures the idea that you have a nicely behaved object. And yeah, in fact, one of these is given exactly by this notion that's already come up of Z stability. So this is a result of Rodem from 2004, which gives you access to a much larger source of examples of cross products that have stable rank 1. So the result is as follows: let A be a simple unital and Z stable C-star algebra. Then A has stable rank 1 if and only if A is finite. Okay, in which case it will actually be stably finite. And otherwise, it's in fact purely infinite. This is not so important, but one very nice consequence of this result is that amongst the so-called classifiable, maybe Elliott classifiable C-star algebras, by assumption, these are all Z stable and simple and unital. And so in particular, you have this dichotomy where all of the finite classifiable C-star algebras have stable rank 1, and then all the other ones are purely infinite. So in fact, there's a very large literature on trying to show classifiability of, for example, cross products. And so you can appeal to this result and deduce that all of the finite ones therefore have stable rank 1. So I won't try to attribute a list of names for results of this nature, because there are many, but let me just give you one example of a consequence of this result together with the results showing Z stability of these guys. If you take G to be any elementary amenable group and X finite dimensional, and the usual assumptions that we make, that the action is minimal, topologically free, and so on, then because this group is amenable, there will always be an invariant measure, so your cross product will always be finite. So then the cross product has stable rank 1. Okay, so the result, of course, is that it's actually Z stable, but as a consequence of Rodem's result, we also know it has stable rank 1. Okay, so already we can see there are close connections between classification and this property of stable rank 1. But as I alluded to before, you should really think of stable rank 1 as a much weaker condition. And in particular, it's satisfied by a lot of non-Z stable, non-classifiable C-star algebras. So, however, there are non-Z stable C-star algebras with stable rank 1, even simple. And these are given, for instance, by non-Z stable Willitson algebras type 1. And also pretty much all of the counterexamples to the original formulation of the Elliott conjecture. Also in the dynamical context, there are examples due to Gill and Kerr of minimal homeomorphisms of some infinite dimensional spaces that give rise to non-Z stable cross products. And these are also known to have stable rank 1, despite being non-Z stable. Right. So that's kind of the lay of the land a little bit. We want to go beyond somehow the classifiable setting and establish stable rank 1 in the hopes that that's still useful to say important things about these examples. All right. So I mentioned that these dual Kerr systems give rise to cross products that have stable rank 1. This is a result of the following theorem. So for integer actions, this is originally due to Alboyu and Lutley in 21 maybe. And this builds on work of Archie Phillips. And let me also add that this is generalized by Li and Yu beyond integer actions, also around the same time. And the theorem says the following. Let, say, Z to the D act on a compact metrizable space, free and minimal. Then the associated cross product has stable rank 1. Right, and the surprising thing about this result is that other than this kind of simplicity condition, there's absolutely no other assumption that you need to make. So in particular, X doesn't need to be finite dimensional. Your action could have positive mean dimension, for those of you who know what that is. And in that way, you can easily somehow cook up examples that fall beyond the classifiable setting, but nevertheless, you get this nice conclusion. Okay. And in fact, this Li and Yu result is something more general. So what they in fact show is that for any amenable group, the conjunction of two other properties of an action. So the first is the so-called URP or uniform Rockland property. I won't get into this exactly what this is, but it's some kind of tiling condition for your action. You can somehow decompose your space in a nice way, and this gives you some nice structure in your cross-product C-star algebra. And the second is called comparison. So here I'm going to use the notion of dynamical comparison. They in fact use something slightly weaker that's a bit more C-star algebraic, but comparison will be also useful later on. And they show that for any action of an amenable group with the URP and comparison, that's also free and minimal, this will give you stable rank 1. And then the reason that there are no other hypotheses in this theorem is that it's also been shown that for Z to the D, or more generally abelian groups, these two things are automatic. Okay, so let me, as I said, I won't get into the URP, but I want to remind you what this notion of comparison means. So we'll take, we'll consider an action of G on X, and we take A to be some closed subset and B some open subset. And we write that A is subequivalent to B, written like so, if you can draw the following picture. So here's my A, here's my B, and A is subequivalent to B if you can cover A with finitely many pieces and then map them by some group elements into B in such a way that their images are disjoint. Right? So somehow, from the point of view of dynamics, A can be compressed inside of B. So it's smaller than B in this dynamical sense. And then we say that the action has comparison if this holds whenever the measure of A is strictly less than the measure of B for all invariant measures. Okay, so if from the point of view of these invariant measures, A looks like it should be smaller than B, then you can actually arrange this in a dynamical fashion to be the case. For those of you familiar with classification, this looks a little bit like a strict comparison for C-star algebras. And indeed, this is part of the motivation behind this definition. Right, but as promised in the title of the talk, we want to talk about non-nuclear cross products. And we immediately have some problems. So comparison is known to hold in quite great generality for actions of amenable groups. The URP for slightly less general class of actions. But the URP already implies that G is amenable. Because you need the existence of fullness sets in your group. So we can't use the URP if we're considering actions of non-amenable groups. And for actions of non-amenable groups, also the question of when comparison holds is, beyond some simple examples, essentially not known. So even if we wanted to use comparison, it maybe doesn't apply to many interesting examples. So these are somehow the two things that, well, one are the crucial bits for Lean use arguments somehow, but also the things that we can't use in the non-nuclear setting. So we need to weaken both of these in a suitable way in order to show something for non-nuclear cross products. Okay. Are there any questions at this point before I move on? Cool. Right. So this is sort of the current state of what's known for stable rank 1 in cross products. Let me take a step back now and describe to you how on earth do you show stable rank 1, right? So there are obviously a number of different approaches, but one of the key approaches, particularly in this dynamical context, goes back to another result of Rodin, which I'll call Rodin strategy. And in a sense, it's just a couple of very insightful observations about the size of invertible elements in a C-star algebra, but it proves to be extremely helpful in showing stable rank 1. So I want to describe a little bit how this strategy goes, and this will be useful in motivating what comes next. So first of all, we'll start with a proposition, which says the following. So A will be just a unital C-star algebra for now. And the proposition is that Z to the D A, so this is the set of two-sided zero divisors in A. So the set of A in A such that BA equals AC equals 0. So A is annihilated on both sides by some non-zero B and C in A. So if I take the closure of this set of two-sided zero divisors, this is equal to the complement of the set of one-sided invertible elements. So this is my notation for one-sided invertible elements. So either left invertible or right invertible. And the claim is that, yeah, the complement of this set is exactly the closure of the two-sided zero divisors. And I want to actually give the argument for this because I think it's quite instructive and alludes to some of the key tricks that go into these proofs more generally. So one direction is not so difficult to see. So let's start by showing this inclusion. All right, so I need to start with, let's say, a two-sided zero divisor. You can check that in much the same way you show that invertible elements form an open set. You can show that one-sided invertible elements form an open set. So its complement is closed. So it suffices just to take something in the set of two-sided zero divisors. And we want to show that this can't be one-sided invertible. So we take an A that's a two-sided zero divisor, and we suppose, for the sake of a contradiction, that it's, let's say, left invertible, right? The argument's the same if it was right invertible. So what this means is that there exist a B and a C in A non-zero, such that, well, first of all, it's left invertible. So let's say B times A equals 1. But it's also a two-sided zero divisor. So this C annihilates A from the right. Okay, but then this implies that C equals 1 times C. And then we can invoke this equality. So this is BAC. And then using associativity, you can see that this is actually 0. But we assumed that C was non-zero, and so we get a contradiction, and therefore we show that this inclusion holds. Okay, the other direction is sort of where the interesting stuff is happening, where we're somehow relating some notion of invertibility to this zero division property. And let's see how this argument goes. So let's fix some tolerance epsilon and A in the complement of the one-sided invertible elements. And then A, we can use its polar decomposition to write it as B times the absolute value of A, where absolute value of A here means you apply the continuous functional calculus to this element A star A. Right, and then we define A epsilon to be V times this so-called epsilon cut down of the absolute value of A. So this again is defined using the functional calculus, and the picture is as follows. Right, this is a positive self-adjoint element. So its spectrum is containing the positive real line. And then my element A, under the continuous functional calculus, corresponds to this constant diagonal function. This is my absolute value of A. And this epsilon cut down is what it sounds like. So you just take 0 up until epsilon and then define this. So this is the epsilon cut down. And now I want, I claim that this element is actually a two-sided zero divisor. And the way to see this is to define another function like so, and I'll call this G epsilon, again defined on the spectrum of this element, the norm of A, the absolute value of A. And we define, let's see, I want to get it the right way around, B as G epsilon applied to A, and C as G epsilon applied to the absolute value of A star. I should say, by the way, that you can check that this is also the same thing as, let's see, A star absolute value minus A cut down times V. All right, but now notice in this picture that if I take G epsilon and multiply it by this other function, it will have to vanish everywhere, right? Because this cut down is 0 in this interval and G epsilon is 0 outside of the interval. So the product is 0. And for this reason, if you compute the products, A epsilon times B, well, what is this? By definition, A epsilon was V times this cut down. B is this G epsilon applied to the absolute value of A. But the continuous functional calculus is a homomorphism. So this product is the same as the product of the continuous functions applied to the absolute value of A, but I just said that this is 0. Okay, and in exactly the same way, you can argue that C times A epsilon also equals 0, where instead you use this identity. And then consider the element, the norm of A star. So in particular, we've shown that this A epsilon that I've defined is indeed an element of the two-sided zero divisors. And again, you can check that, as the name maybe suggests, this element is within distance epsilon of the original A. And therefore, because epsilon was arbitrary, A will belong to the closure of this set.
But yeah, very working the fact that there were anything getting in the complement of the.
That is a great question. That's a very good question. Where have I used it? Right. So I used yeah. In a sense, I haven't used it. I've just said something that's not very important. So in this point, exactly, that's the point. So yes, thank you for clarifying. So up to this point, everything I've said works completely generally. It's just that these two could be 0. Right. So since norm of A and norm of A star are not invertible, 0 will belong to the spectrum of both of these elements, and that has the consequence that B and C are not 0. Yes, thank you. That's a very important point. And you can see that somehow, if this wasn't the case, eventually you'd run into a problem as you took epsilon to 0. You could go to somewhere where the spectrum of your elements actually beyond that. Okay, so that's the proof of this. So this is the first important observation. The second is really more of just an observation. If for a given element A, there exists a unitary U in A such that U times A is nilpotent. So by this, I just mean that element raised to some power equals 0. Then A belongs to the closure of the invertibles. So let's unpack this a little bit. First of all, if an element is nilpotent, you can check that its spectrum has to be 0. And that means that UA plus a small scalar multiply of the identity will be invertible, because its spectrum will be exactly this, let's say, non-zero element lambda. So this is invertible for every non-zero lambda. And as you take lambda closer and closer to 0, this will approximate this UA. Okay, so nilpotent elements can be approximated by invertibles. And then the point is simply that multiplying by a unitary doesn't change whether or not you're invertible. And so you can multiply by U star to undo the unitary, and this will approach your original A. Okay. So the consequence of all of this is the following. Let A be simple, unital, and finite. if you can show that for every, what do I want to say? If the set of two-sided zero divisors is contained in the closure of the invertibles, and I should stress that, I mean, this observation is meant to give you the tool that you use to show this, right? I give you a two-sided zero divisor, just find me a unitary that rotates me to something nilpotent. This will show this condition. If I can do that, then A will already have stable rank 1. Why is this? So it's a consequence of this previous proposition. So if you have this inclusion, so this together with the proposition implies that A take away the closure of the invertibles. This consists precisely of the non-invertible but one-sided invertible elements. Okay, so there's a little bit of playing around with the set containments and so on, but we're taking away the closure of the set of invertibles. So certainly there can't be any invertibles in here. But if this is contained in here, and the closure of this set is the complement of the one-sided invertibles, then this actually must contain all the one-sided invertible elements. So it takes a moment's thought to pass this fact, but it's true. And then the point is that this finiteness assumption finally comes into play because it tells us precisely that this set is empty. Okay, so in fact, A coincides with the closure of the set of invertibles, but that's exactly what it means to have stable rank 1. Okay. Yes.
Sorry, who said again? Why does this affect?
Right. So because we're assuming A is finite, there are no one-sided invertible but non-invertible elements. So this set is empty. So A is equal to the closure. And this is exactly what it means to have stable rank 1. Cool. At this point, I will move to some slides. So I've kind of explained maybe the outline of what we want to show. Oh, I see. Yeah. So need to turn off the light. Right. So as I've explained, we're in the situation where we have kind of the outline of what we want to do. I want to give you a two-sided zero divisor in my cross product and find a unitary that rotates this element to something nilpotent. And one of the things we do in this paper is introduce somehow precisely the dynamical condition that allows us to do this in the cross product. And this is a notion that we call square divisibility, which I'll try my best to explain through these pictures. So we say that an action is squarely divisible if the following picture can be arranged. So this is meant to represent my space X that I'm acting on. So I have this n by n grid of open subsets. And maybe from now on, I'll just assume for simplicity that X is the Cantor set. So you can maybe think of this as an actual partition of X. So I've got this n by n array of, let's say, clopen subsets of my space together with this remainder term. And these should all be pairwise equivalent and pairwise disjoint. in a way that somehow behaves like matrix units. And then we need the following 3 conditions to hold. Oops. So
Equivalent would be like dynamical.
in a dynamical sense, yeah. Maybe I need to click on the screen. Oops. Okay, so the first thing that I need to happen is that in each row, if I take the first Clopin subset, that this should be dynamically subequivalent in the sense that was described before to some part of the rest of its row. Okay, and this should happen for every row. So in a sense, the levels are small in the sense that one of them can be absorbed into the rest of its row in this dynamical sense. The second thing is that the remainder should be small in the sense that the remainder can be dynamically absorbed into some other disjoint part of the array that also, I should say, misses this sort of dynamical boundary, which I won't get into, but somehow it should be in the dynamical core of these sets. Okay, so the remainder should also be small. And then finally, this dynamical boundary should also be small in the sense that it can be absorbed into the remainder. Right, so this is a lot to take in. Unfortunately, this is about as simple as the picture can get. But as I said, it should be precisely like the minimal thing that needs to happen in order to arrange this rotating by unitaries picture. So let me describe to you what ends up happening when you have this square divisibility.
Sorry.
Yep.
What is this dynamic?
Yeah, it's so somehow you can take your set and some finite subset of your group. You can look at all the translates of this, and then you look at kind of the intersection of all of those. So it's the bit that's really like fixed under the dynamics in some appropriate sense, right? So it'll move around a little bit under some given fixed subset of your group. The interior of this, the bit that really stays completely fixed, this is the complement of this boundary. It's the boundary sort of everything else intersected with your original set. Yeah. Okay, so what does this translate to C-star algebraically? So first of all, I give you an element A in the cross product that is a two-sided zero divisor. You can check playing around with this conditional expectation that it suffices to take this element witnessing the two-sided zero division to be, in the case of the Cantor set at least, the indicator function of some Clopin set. Okay, and then these 3 subequivalences that I've described give you 3 unitaries, U, V, and W in the cross product. And you can conjugate this original element A in some way by these unitaries. Okay, the order is not so important. But then because I've got this partition of my space X, I can write the unit in the cross product, which is the indicator function of X, as a sum of indicator functions of each of the elements in my decomposition. So I get kind of a partition of unity, if you like. And then writing this element B as 1 times B times 1, I can think of B as this matrix array. And then my claim is that these unitaries are very carefully constructed so that when you express B in this matrix picture, you have exactly spread out sufficiently many zeros coming from this first equality here so that the somehow matrix you end up with is nilpotent. So from the first subequivalence, this was the one sending the first element of each row into the remainder of its row. Yeah, this corresponds to the zeros that I've indicated in the matrix. So we get already a bunch of zeros from the first subequivalence. From the second subequivalence, this said that the remainder can be absorbed somewhere into the array where the zero division is happening. So you get this first column of zeros. And then crucially, and this is where this kind of bizarre dynamical boundary property comes into play, the fact that it can be sent into the remainder tells you that everywhere else there's also zeros. So the only non-zero elements that could exist in this matrix decomposition of your element are indicated with the stars in this matrix. And it's maybe not a big step to believe that if this really was a matrix, you could conjugate this by a couple of other unitaries and move everything to the right and move everything up so that you actually get this strictly upper triangular matrix. And we know that strictly upper triangular matrices are nilpotent. And so we've achieved our desired goal. We can then take this element B, which we've shown can be rotated to something nilpotent, undo all of the multiplication by unitaries, and this tells us that our original A can also be approximated by invertible elements. Okay, and this is the very quick version, but hopefully that made some kind of sense. And now I will maybe end the slides, go back to the board. Right, so what's the point of all of this? Why go through all of this hassle? Well, if you believe that very hand-wavy explanation, we get the following theorem. Suppose that we have an action, same assumptions as before, minimal, topologically free, and so on. And suppose that it is additionally squarely divisible in this sense that I've described, then the reduced cross product has stable rank 1. And the proof is somehow exactly unpacking the picture that I've tried to illustrate, that this Rawdon strategy really unfolds in the way you hope in the cross product. Okay, so this is nice, but of course you might be tempted to say this would surely just never happen for an actual action that I write down because it's so complicated. It turns out that with quite a bit of work, you can actually show that it holds, and so this is actually a useful theorem. So the first consequence is we recover in a way that replaces Lee and Yu's assumption of comparison of open sets by dynamical comparison. We recover their result in the case of amenable group actions. So, and in fact, we obtain a generalization where we can also take products of actions of this form. So I'll take one action where the first G is amenable. And then the second can just be any action, in particular, an action of a non-amenable group, but along with the usual assumptions we make that they're minimal, topologically free, and they preserve an invariant probability measure, then the product action so this is the thing you imagine where it just acts component-wise, G acts on X and H acts on Y. This action is squarely divisible. I should also say, of course, we want to recover Lee and Yu's result. We also need this URP plus comparison. Okay, but if you like, you can just pretend G is Z to the D or an abelian group, and then you can ignore those extra assumptions. Then this product action is squarely divisible. And the associated cross product has stable rank 1. Okay, so in particular, forgetting about this action of the second group on the second space, we exactly recover Lee and Yu's theorem in the case of amenable group actions. And by taking this to be essentially any action you like of a non-amenable group, preserving an invariant measure, you can also construct actions of non-amenable groups whose cross products still have stable rank 1. Right? But this is a little bit unsatisfying because we're kind of cheating by using this first factor being amenable and having all of these nice tiling properties and comparison properties and so on. What we'd really like is just to start with a given action of a non-amenable group and deduce stable rank 1 for those cross products. And in general, this is very difficult, but the approach that we've taken is to show that somehow for nice spaces of actions, this holds generically. So somehow in a certain topological way, if I pick a certain action, it will very likely have stable rank 1. The cross product will likely have stable rank 1. So let me quickly describe what's going on there. So I'll write WA. So, okay, this theorem here is completely general, just all the usual assumptions that we've made. From now on, X will be the Cantor space. And somehow for these bare category type of arguments, it's very important that we have the flexibility of working with the Cantor set. So this will denote the set of actions of the free group on the Cantor set that are minimal, topologically free, have an invariant measure. So again, these are our simplicity assumptions. This is our finiteness assumption. And we also ask that they are weakly mixing. Which I won't define, but it just says that somehow the dynamics are not boring in the sense that you don't have quotients onto actions on finite sets. So you want kind of sufficiently non-trivial action. And I'll elaborate a little bit more on why we make that assumption in a second. But then the theorem is that for a generic, so by generic here, I mean on a, so there's a certain Polish topology that you can place on this set of actions. And then generic means that on a dense G delta subset of this space, for a generic action in this space, the associated reduced cross product has stable rank 1. Okay, so these now are really genuine actions of the free group. We can't cheat here and just use the product with an amenable group action. Now you might say, well, why are you making this additional assumption? Surely the thing to consider would just be this whole space of actions completely arbitrary. And the point is that if you did that, in fact, there's a single generic action in that space, which is the so-called universal odometer. And this we know already for other reasons has a cross product with stable rank 1. And so if we want to treat really distinct and new actions that give stable rank 1 cross products, we make this essentially to rule out this one conjugacy class in the space of all such actions. One unfortunate thing about this theorem is one of our goals was to cover a large class of actions, but we don't know if a similar thing happens in this space. We strongly suspect not, but it could be the case that there's also a single generic action in this space, in which case the theorem is not so exciting because you're just saying for that one action, we have stable rank 1. But we can remedy this by working in a different space of actions of free groups. This set A star, and this is the set of actions of free group on the Cantor space that are topologically free, preserve an invariant measure. And then this is an action of a free group. So each of the generators corresponds to an integer action. And we ask that each of these integer actions give you a, let's say, strictly ergodic, which means it preserves exactly one invariant measure and is minimal. and sort of weak mixing in a certain sense for this Z action. You can get away with something slightly weaker, but weak mixing is fine. Then in this space, again, we can show that for a generic action in the space, the cross product has stable rank 1. And moreover, the conjugacy classes so by this, I mean, take an action in the space, look at all the other actions that are conjugate to that one, and then consider that as an equivalence class. The conjugacy classes are all meager. So sort of the opposite of generic. These happen for a nowhere dense subset, or maybe union of nowhere dense sets. And in particular, what this tells you is that you really capture many, many distinct up to conjugacy actions whose cross product have stable rank 1. And yeah, I think I'll end there. Thank you very much.
Questions for Jamie?
Thanks. If you take the group to be the integers, is it easy to see that if you take an integer action that it's squarely divisible? Is that something you can show?
I would say no. So I mean, the point is that for, as you say, for actions of the integers, that the operative assumption is really this URP in comparison. And in that setting, really our approach is very much analogous to the approach of Lee and Yu. So you start with this decomposition you get from the URP and combine it with comparison in a certain way to get to follow this strategy. The difference in the case of square divisibility is somehow this different scales. So there were these 3 levels of subequivalence, right? The remainder had to be small, but it couldn't be so small because it also has to absorb some other part of the tower. And so there is indeed a way of taking the URP that you get for integer actions and sort of slightly rearranging this tower decomposition in a certain way to witness square divisibility. But I would say it's no more obvious than showing URP. And in fact, there's something a little bit more to do because you need even something a bit more restrictive than the URP. So yeah, it'd be difficult really to take inner rational rotation algebra and write down what this array looks like. But you can use this abstract machinery of the URP and some kind of Ornstein-Weiss type machinery to rearrange this and force it into the picture that you want. So in a sense, there's a trade-off. This square divisibility condition is beautifully designed to make the proof of stable rank 1 go more directly. But then, of course, verifying the condition dynamically is more difficult.
Oh, okay. Not like you just take a bunch of open sets and move them around.
No. Yes. It's quite the balancing act to get exactly the right thing you need.
Okay, thank you.
I'm interested in another regularity property which you have not mentioned. So sorry if this is a bit derailing. Exactness. So do you, like, for example, the free group, if you take the cross product, this will be exact. But the way I think about this is because you can write it as a free product of integer actions and blah blah blah, and then there's this Dykma whoever result. But do you know, is it true in general? You have an action of an exact group. Do you get an exact cross product?
I don't know anything about this.
Okay, fair enough. Okay, yeah. Fair enough.
Yeah, I'd be surprised if any of this technology would help in answering that question. But
Right. Yeah, sure. Yeah. Because I mean, I was just wondering, like, what, so you could apply this theorem here on the bottom left to of a variety, as you said, of a variety of non-amenable groups, like by the way, Ray, like SO3 would be, so anything that contains the free group will be non-amenable because non-amenable would pass. So this is how you prove the Banach-Tarski paradox. You exhibit the copy of F2 in SO3, and you. Right, I guess so. Yes. Anyway, so you could plug in SO3 or whatever in this, and yeah, I wonder if that would be exact. I don't know.
yeah, I'm not sure.
Okay.
Maybe one thing to say about this result is that in particular, this sort of absorption of arbitrary product actions. As you noted, these products C-star algebraically end up being tensor products. So this will be the isomorphic to the tensor product of the first action with the second. And suppose, for instance, that this action gave you a Z-stable C-star algebra. Well, then trivially, the resultant tensor product will also be Z-stable, and it'll be finite under the other assumptions, and so it will have stable rank 1. What's surprising is that when you go beyond Z-stable things, showing this preservation under tensor products is actually quite a difficult problem. So it's still open whether if you have two simple C-star algebras with stable rank 1, will their tensor product have stable rank 1?
Right.
And yeah, there are sort of similar results in the literature where beyond Z-stable things, trying to show such a result is maybe more subtle than you would think to begin with.
Maybe I'll also ask, have you had any thoughts about non-commutative versions of this technology?
Yeah, I think so there is some literature on this. Mostly it's restricted to like actions of finite groups on non-commutative things. And even there, I mean, you can sort of get some upper bounds or something like this for stable rank, but in general, it's like much less is known, I would say. And for like actions of infinite groups, very little, I think. Somehow the extra flexibility of acting on a space is quite important. And it underlies all of these tiling type of arguments. So another thing you might hope to do is do something at the level of generality of groupoids or something. But again, we don't have this Ornstein-Weiss machinery somehow coming from amenability somewhere to make the same argument work. So really, it's quite special to this particular context, I would say.
Fair enough. Thanks.
So in your last two theorems there, you wrote that for these guys, your cross product is stable rank 1. But you're actually showing that those actions are generically squarely divisible? Is that the idea?
Exactly, yeah. So you combine the two theorems together, you check that these generically have square divisibility, and then hence the cross products is stable, have stable rank 1.
And for this, because for the second guys, there's unique trace, I guess?
Right, exactly, yes.
I wonder if you could show something like this selflessness property or something in that case.
Yes, that's certainly a very good question. That's something that I would like to be able to show. So, I mean, this in a sense gives some evidence that that's a thing we hope for.
Yeah,
right?
exactly.
And for sure, that's one of the directions. You could go also trying to show strict comparison, for example, for some of these, or pureness, something like this. I would say that's definitely a good thing to look at. But for now, already getting stable rank 1 is quite hard.
Sure, yeah.
Yeah.
The reason why in the last case the conjugate sequences are given, is it something simple or?
It's not something simple. It's some actually it uses some very surprising tools. So you somehow need to go via this machinery of studying orbit equivalence of Cantor minimal systems. And then with each strong orbit equivalence class of such an action, you can realize different values of entropy. And then you can kind of play off zero entropy with positive entropy to to argue that the conjugacy classes are meager, but this is sort of very specialized to make this work and requires all sorts of tricks from ergodic theory and dynamics to show it. So it's, I would say, very non-trivial, and it's part of the reason why, in this case, we don't know whether the conjugacy classes are meager because, we don't have the same tools, and here we can kind of work just by focusing on a single generator, right? We can take one of the Z actions corresponding to a generator, play around with this guy, but yeah, in this setting, it's much harder. And for instance, you can get many different invariant measures and trying to, so somehow you want to take one of the generators, perturb it slightly to some other action, but in the process of perturbing it, you might fall outside of this set again. So you might no longer preserve an invariant measure for the whole action, or you might no longer be minimal for the whole action and so on. So it's quite a subtle point to try to get this meagerness. Yeah.
There are no further questions. Let us thank Jamie once again. And we'll see you all next week for seminar talk by Konrad Aguilar.